Okay, let's continue number 9 and 5.4. So recall our eigen values that we obtained were 4i and negative 4i, so definitely complex numbers. And from our eigenvalue method, so we basically did step 1. And now step 2 is we need to attempt to find so n, or in this case, 2 linearly independent eigenvectors, so v1 and v2, that are associated with these eigenvalues. And then we can, if they are linearly independent, then we can definitely construct some nice general solutions that involve our exponential functions, which are very, very powerful in just a lot of applications. I mean, we definitely have been working a lot with, e to the r1t, e to the lambda 1t, and so forth. Okay, so let's continue. Let's go ahead and find our eigenvalue, our eigenvectors. So let's just go ahead and start with lambda 1. So if lambda 1 is 4i, then what's our associated eigenvector? Well, we're definitely going to use a relationship that, so let's go ahead and write then a minus lambda, I'll go ahead and write 1i times our vector v, right? This is our eigenvector that we would like to find, so I'll just call it v1. And again, we can just substitute our coefficient, right, minus the lambda 1 that we know. So there's our lambda 1, so we're just going to insert that guy in there. And okay, so we have, what was our coefficient matrix? It was 2, negative 5, 4, negative 2, minus lambda I. Okay, so minus 4i, and then I get our identity matrix, so 1, 0, 0, 1, and there's no determinant obviously here, times our vector v. Again, this guy is bold, so if you want to write the little arrow there, equals 0. Okay, so here's just some, again, college algebra matrix operations, right, scalar multiplication. So 2, negative 5, 4, negative 2, I'm just repeating, and plus, and if I multiply, right, the scalar inside each entry, I get negative 4i, 0, 0, negative 4i, and I should be careful here. I should really have extra set of parentheses. If you used the curvy parentheses, then this would be brackets, but since I used these rectangular brackets, then I would use the brace after, just by convention. Let's see. Okay, so we have, this guy, v equals 0. Okay, and then we're just adding matrices. So I have 2 minus 4i, right? This guy, I'm basically just adding those guys. Negative 5, right? This guy and this guy, and I'm doing 4 plus 0 is 4, negative 2, negative 4i. Okay, so there is my 2 by 2 matrix with complex entries times our vector v, right? And let's go ahead and, well, let's just go ahead and write it like this so far. Okay, so hopefully it's making sense so far. So now we want to solve the system for, our goal is to find our eigenvector, right? Because these are real numbers. Well, I should be careful, complex numbers. The unknown here is our v, and actually, just to save some steps here, so I'm going to erase this. Well, it's not letting me erase it. Okay, let me just write it again. So 2 minus 4i, 4, negative 5, negative 2 minus 4i, and then I'm going to go ahead and write my my vector, my 2 by 1 vector, right, as v1 and v2, right, because that's what this really means. Okay, equals 0. Okay, so now we want to translate this back into maybe a system of linear equations, because we know how to solve systems of linear equations. It's especially two equations in two variables, right? We just have complex numbers here. So let's go ahead and, so this translates to, right, so we have again our AX here. Let's write this as, okay, 2 minus 4i, let's see, v1 minus 5v2. So what I'm doing here is I'm doing matrix multiplication. I'm multiplying the row times the column, and then this row times this column. So it's this guy times this guy, which is this, and then this guy times this guy, and then similarly we can do the second row. So we have 4 v1 plus negative 2 minus 4i v2, right? So this is, I just translated into a system of linear equations, right? It's the same thing, just a different form. And actually, just to be careful here, I want to, I'm going to write, I'm going to call this x and y. I'm going to call this x and y. Just to, it helps remind you that we're actually working with linear equations, or, well, linear equations, but in this case a linear system because we have more than one. Okay, so here, so we've used our eigenvalue for I, and we've generated the system. And the goal is to solve for x and solve for y. Now this is, you're just doing an algebra problem. The only difference is you're working with complex numbers. Okay, now I want to quickly show you something. I think that's very, hopefully not, I don't think it's too hard, but it's very powerful and it saves a lot of work. This line is actually the same line as this, as the second equation. And so if you didn't know that, or you don't see that it's a multiple of each other, and it's sometimes a little bit difficult when you're working with complex numbers. But I'm just going to do some algebra, and I'm going to solve for y here. So if I solve for y there, right, I'm going to bring my 5 y over and then divide by 5. I obtain y equals 2 minus 4i divided by 5x. Okay, so I'm solving the system by substitution. And so this is my expression for y, so then I'm just going to substitute it back into the other equation. And we have 4x plus, and I have this guy, times 2 minus 4i over 5x equals 0. Again, remember when you solve systems of linear equations in algebra and they're real numbers, right, you're basically finding the point of intersection, or if they're parallel lines, or if they're the same line, which is infinitely many solutions. So here we can kind of make this look a little bit nicer. I'm going to go ahead and factor out a -1 from this guy, because we can. Plus 4i, and then I'm just keeping this guy the same. And the reason I did this is because, right, these guys, I mean, this is a conjugate of this complex number. So, I mean, this is a plus bi and a minus bi. You can FOIL it out, but we know a plus bi times a minus bi is really just a squared plus b squared, so that's 4 plus 16, all divided by 5, x equals 0. And then we get 4x minus, okay, that's 20, divided by 5 is 4x. So we get 0 equals 0, so I did not get a specific x or a y. So this is a true statement, which means, whoops, the two equations above, right, have infinitely many solutions. Now it's hard to graph this because we're working with complex numbers again on the imaginary axis. But if this was real numbers, you know, you're graphing the line, I don't know, let's say that was the line, line 1, and you graphed the other line, well, it would be the same line. So they have the same, you know, solution set. You know, this point satisfies, you know, line 1. This point satisfies line 1, but also satisfies line 2. So again, there's infinitely many points in this case, which is very nice because then we don't have to, I mean, we know we can work with any equation we want. We don't have to work with them separately because they're really the same thing. Okay, so now that we know that's true, I'm going to go back here and I'm going to rewrite this guy, 5y2 equals 0. Okay, so we have infinitely many solutions here. So I just need one, and that's not y2, it's just y. I just need one point. Okay, so you can pick, when it's infinitely many solutions, right, any of these guys are going to work as long as the point is on the line. So I'm going to let x be 5. Now you can let x be 100, 3,461, 1, negative 13, it doesn't matter. Now I'm choosing 5. I see a 5 here and I know something nice is going to happen. So if I substitute my 5, okay, so minus 5y equals 0. Oh, might as well show all the work here. It's just some algebra, equals 5y. And my 5's are going to cancel, right? I mean, I'm going to divide by 5, and I'm just going to get 1. So what do I get? Y equals 2 minus 4i. Okay, so my input was 5, and my output was 2 minus 4i. Okay, so what does that mean? Well, that means that our associated eigenvector, right, to our eigenvalue 4i is the following. So we know this guy is going to be v1, and it's really just the x and the y. So I let x be 5, and then we obtained 2 minus 4i. Okay, now if you chose 6, then again, you're going to get a different output. If you wanted to let y be something, I don't know, y be 5, well, you could let y be 5, then this would be different. So again, these are, if you're working with somebody else, and you're not going to get the same components unless you choose the same input or the same output. But again, this is your imaginary or complex point or vector on your complex plane. Okay, so that is our V1, and again, let's look at the big, let's not lose sight of the big picture, the goal of the big picture, which is to find a particular solution, but more specific, well, we have to find a general solution first. And from page, let's see, let me write this down, page 374 in your book. So we're talking about, we have complex eigenvalues, right? Or they come in obviously in conjugate pairs, which is a little different than real numbers. So the theorem 1 is not going to work exactly with a complex number. It's similar, but I mean, we have complex numbers, so we're probably going to use, we're going to have a real part and an imaginary part. So I'm going to go ahead and do this in the next video since it's about 14 minutes already. So again, I'll start up with page 374 if you'd like to kind of see the different equations that I am using.